here for unlocking the potential of 120-volt heat pump water heaters, field study findings and future outlook. Our presenters from Slipstream are Dr. John Koliner and Dani Ball. As usual, materials and resources from CREATE are available at createenergy.org, along with additional information about other upcoming workshops and presentations and webinars. Specifically, there's another webinar coming up tomorrow at 9:30 a.m. and also May 2nd on Friday. Low-cost gas laws demonstrations using Arduino, and tomorrow, turning students into energy leaders. Our presenters today, heat pump water heaters, Dr. John Koliner and Dani Ball from Slipstream. Dr. John Koliner is a Director of Research and Innovation at Slipstream, where he studies emerging electrification and decarbonization technologies through field studies and market assessments. He has been doing research, evaluation, and planning work on behalf of utilities and program administrators for over 10 years. His primary interest is in residential technologies and approaches that enable whole building electrification, including heat pumps for water and space heating, combination systems, and panel optimization. Dani Ball is a research analyst at Slipstream, where she leverages her analytical and data storytelling skills toward residential electrification research. She holds a degree in civil engineering from Princeton University and has previously worked in conservation, architecture, and policy. I can tell you I'm personally especially glad for the workshop today. I've been doing a little bit of work with Sketchbox, an energy modeling tool from Slipstream. And one of the things that I talk with my students is about electrification of buildings. And so I'm especially excited to see what we're going to learn today. I'm going to turn things over to our presenters. Thanks for being here, everyone.
Yeah, thanks for having us. All right, let's see how this works. Can everybody see this nicely? Cool.
Yep.
Hi, I'm John. I am a researcher, a director of research at Slipstream. Dani is here presenting with me, and we're presenting on the results of our Midwest 120-volt heat pump water heater study. We were supported in this study by Focus on Energy, ComEd, Consumers Energy, and Excel. So thanks for having us. So here's the agenda items. We're going to talk through what we were trying to find during this study, some results from talking to installers of this technology, how we did our research, how these units perform, some customer satisfaction results, and then we'll give some recommendations on how to use this technology in the future, and then open it up for questions. This is a pretty massive research study across the Midwest, funded by 4 entities in 3 different states. And it actually happened in 2 phases. I'm primarily going to be talking about the second phase, where we went and installed a bunch of heat pump water heaters and looked at their performance. But actually, the lead up to that phase was phase 1, where we talked to manufacturers and distributors to understand whether 120-volt heat pump water heaters would be a good fit for the Midwest. But then in phase 2, we went out and started installing them and monitoring them to see how they performed. Okay, I'm going to give a little overview of the study and the technology. So for those of you who are not even familiar with heat pump water heaters generally, they're electric water heaters that have a heat pump that pulls heat from the air around them and puts it into the water. So instead of like a natural gas water heater that's burning gas to heat the water, this is pumping heat using electricity to put heat into water. And a typical unit has that heat pump, which is a little bit small for meeting a home's water heating needs, and then also has an electric resistance element that can serve as backup to boost the heating power when necessary. Those units they require a 240-volt circuit. So typically when somebody wants to install those units, they have to get an electrician to come to run a line if they're replacing a gas unit, which won't have a 240-volt circuit there. Which brings us to this technology. So 120-volt units can be plugged into a standard outlet when they replace a natural gas water heater. What that means is that, if you're looking to swap it out, you don't need an electrician to come and run a circuit, which can save you quite a lot of money. And if you are looking to electrify your home and you find that your panel is constrained, it can be, north of $10,000. In a typical situation, it's $500 to $1,000 it'll save you. In order to make sure that these are providing enough hot water, the typical recommendation is to upsize the units. So if you have a 50-gallon, they recommend you switch to an 80-gallon unit to hold more hot water. And also they recommend that you install a mixing valve that basically you can heat up the water in the water heater to a higher temperature and then blend it down with cold water from the ground to get to something like 125 at the faucets. That way you can store more heat so that it can provide for your hot water needs. And the reason why they're a little underpowered is they're, operating off of that 120-volt 15-amp circuit as opposed to a 240-volt 30-amp circuit that's almost 4 times more powerful and can have that backup electric resistance. So these reduce home electric upgrade costs, don't require an electrician, and are generally just as efficient as their 240-volt cousins that are kind of the typical heat pump water heaters you would envision. For this study, we went around installing these in the Midwest. We had to recruit 27 single-family homes in 3 states. 25 of them had a pre-existing natural gas water heater. 1 had a propane-fueled water heater, and 1 had an electric resistance water heater. Although I will note that it's not recommended to replace an electric resistance water heater with one of these units because you will already have a 240-volt line running to that water heater. So you might as well get the 240-volt heat pump water heater that has the backup element. We did outreach through a bunch of channels, recruited all of our participants in a variety of ways in different territories. We had several manufacturers that provided units who we did consult with about the proper installation scenarios for their technologies. We had 8 Rheem units, for shared circuit, we had 8 Rheem, 10 A.O. Smith, and 1 Nile unit. And we followed the best practices of upsizing by 2 sizes and installing a mixing valve. There are also a type of unit, these dedicated circuit units, where it plugs into a standard outlet, but it is assumed that that outlet is only serving one appliance. You might notice on your panel that you have a circuit labeled washer or water heater or something like that, and that circuit is not supplying power to lights or other outlets. That's the assumption with these dedicated circuit units. And what that means is that they can have a more powerful heat pump on them to heat water faster. But you really can't have anything else sharing that circuit with them because they'll use that full 15 amps on the circuit. In many cases, we did have to do some electrical work with those, mainly because we were doing virtual walkthroughs with these sites. And so it wasn't 100% certain with a participant whether they truly had a dedicated circuit until we got on site. We had 6 installation contractors across the 3 states. And what we learned was that many smaller contractors actually couldn't even hold, an extra heat pump water heater in their shop. They often didn't have shops and didn't have room. So we had to work with distributors. We had minor electrical work in many cases, although we expect that in the field, if you have an installer going on site and they have access to this technology, they would only really bring it if electrical work was not required. And a big takeaway was that installers really need to understand the surrounding space around the water heater. Because these exchange heat with the air around them, they need to be in a big enough room to exchange heat with. And if they're not in a big enough room, then ductwork to a different space is required. And installers should confirm that ahead of time before they bring these units out. So we went on site with these installers because we were installing our own monitoring equipment. And we conducted interviews with them after the installation just to see how their experience was. Many of them had already installed heat pump water heaters in the past, although not 120-volt units. But all of them reported that the installations were pretty quick in most cases. The one big thing that caused a hitch was that if space was constrained for either the physical upsized unit, it's a bigger tank, so it's harder to fit in the space, or the room itself, space could be a concern for the installers. Installation time was relatively short, under 4 hours in most cases. Split system installs were challenging. Those Nile units are split systems where the heat pump is actually separate from the tank. And anything besides the installation of the unit itself, the expected kind of installation tasks did add some time to the installs. So we have a little graph of which tasks were required here. The bottom two tasks were required a lot of the time, the condensate drain line and the capping of an existing flue or vent, but those take very little time. The rerouting of pipes and electrical work done by an installer did add time and cost to the installations, and you can see that that was happening in about half of the installs. I'm going to pass it to Dani to talk about the methodology.
Yeah. So first I'll kind of go over what we were measuring to monitor these equipment's performance. So on the next slide, these photos are showing our monitoring setup. So each of these wires going into that box is measuring something about the heater. We had a temperature measurement for the incoming groundwater, a temperature measurement for the outflowing water. We are measuring water flow through a flow meter, and then we are measuring room air temperature kind of right next to the heater in the middle of the room, and then at the boundary of that room, and the living space beyond that. We are measuring air humidity at one location in the room, and then we are measuring the power draw of the heat pump water heater as well as some qualitative measurements that we'll also get into. This is an example of what the incoming data would look like. So this is a day's worth of data. In the middle, you can see the water consumption. So that's measured by the flow meter. And when that water consumption peaks, the water temperature, which is in that top panel of the chart, spikes up. So the hot water kind of goes down to around 90 degrees when it's just sitting there. But then once somebody's consuming it, that's spiking upward to be delivered kind of at set point. This shows why we only analyze energy use and efficiency kind of per day, because that power in the bottom panel kicks on at times that are not kind of in synchrony with the water consumption. So you want to look at the water consumption over a day versus the power consumption to keep that water ready to be delivered over that day. Next, we'll be looking at some general operation statistics of each of the units. First, we looked at people's set points. So that was kind of the most basic number that we collected at the beginning of the study and the end. The blue dots are showing what people's set points were set at by the installer, and then the green arrows are showing where they changed that to throughout the duration of the study. So on average, people raised their set point by about 3 degrees. Next, we have some average water and power consumption bar charts by site. So the power consumption, for the most part, scales with water consumption. There's a little bit of a difference there because the dedicated circuit units are consuming more power because they're able to deliver that power quicker. That's the benefit to those units. Another thing to point out here is consumers 04 on the very left-hand side of the water consumption. This site had kind of notably high water consumption, and this site is the one that we'll talk about going forward, As the one site that this heater was not meeting their needs, they ended up switching away from the 120 volt unit. We looked at the electric resistance of the 10 A.O. Smith units. So some 120 volt units do have an electric resistance included. However, these are only activated in emergencies. So A.O. Smith's documentation says that this is when the air outside the unit is less than 37 or the water is less than 55. And this kicks on a lot less than in a 240 volt unit. So 240 volt units operate at ER 2.6% of the time, versus these 120 volt units, the ER was only activated 7 total times throughout the study. But there is a benefit that this can kick in if the heat pump breaks. This happened to one participant, and they were pretty happy to be able to have this backup power while they waited for the heat pump part of the unit to be fixed. As I mentioned, we were measuring the room temperature and the humidity within the room. We measured that room temperature at 3 locations, and you can see the impact of the heat pump compressor on that in the bottom left. The impact was the greatest closest to the heater, and then as you got further away, there's less of an impact on temperature. There's less of an impact on humidity of these heaters, and the only real measurable impact was during the summer months when the humidity was highest to start with. So that's that green line at the top. You can see there's a bit of a dip in humidity after the compressor kicks on. One of the things that we were looking at was hot water availability. So we measured this according to runouts. And we defined that as a draw in which the water temperature was below 110 degrees. One thing to note is that people may not have kind of experienced every one of these runouts. They could have happened when the dishwasher was running. Somebody might not notice 110 versus 120 degree water. But we measured them on 1 out of every 20 days per site. Sites with higher consumption had more runouts, and more runouts occurred when groundwater temperatures were lower. So the chart on the right kind of shows the combined effect of this. That orange line is showing all runouts or all draws for which somebody had consumed 75 gallons in the 3 hours up to that point. And so this is showing that if you're consuming a lot of water before the current draw, then you're more likely to run out of water. However, all of these lines, except for the below 25 gallon line, slope upwards at lower groundwater temperatures. So this kind of shows that at those lower groundwater temperatures, the recovery time is longer of these units, and so you're more likely to be running out of water later on. For energy use and efficiency, we looked at runtime per gallon. This is related to what I was just talking about. There's a longer runtime per gallon at the lower groundwater temperatures because it takes longer to heat up that colder water to set point. There's 2 clusters in this right-hand chart. There's the dedicated circuit units and then the shared. And the shared circuit units, you can see because of their weaker compressors, they have a longer runtime per gallon, all the way up to 11 minutes at those coldest groundwater temperatures. One thing to note, though, is that the dedicated circuit line is still above the recovery time of a gas unit or a 240 volt unit, but it is significantly faster than the shared circuit unit, which is a plus if you need that. So we looked at the demand over the course of a day for water and for hour for these participants. The water demand on the bottom left, you can see peaks in the early morning and then peaks in the evening. That's the salt lid line, and then the dotted line is for a weekend. So in the weekend, the water demand peaks a little later in the morning as people sleep in and is a little more spread out. The power demand followed the water demand for the most part. And we broke this out into shared versus dedicated circuit because dedicated circuits are pulling more power in order to recover quicker. We also modeled this according to groundwater temperature. So you can see that those green lines are showing the power demand for these units at the coldest groundwater temperatures, and then the blue is at the warmer groundwater temperatures. And all of these have kind of a peak in the morning and a peak at night following the water demand peaks. We looked at coefficient of performance, so how much energy had to be drawn by the heater in order to get a certain amount of energy kind of imparted into the water. The daily COP average was 2.4. This is below the manufacturer UEFs, but there was correlation between the units with the higher rated UEFs performed higher. So on that chart on the top right, this is showing daily COPs for each site. And then those blue dots are showing the rated UEF for each of these units. COP correlated positively with consumption up until about 25 gallons a day. It correlated a little negatively with groundwater temperature and a little positively with inlet air temperature. So these two effects combined meant that there was little seasonal variation in COP. We calculated the energy and cost savings for participants. People saved 87% of the energy use of their prior heater. However, they saved about $7 a month. This is because natural gas is pretty cheap. The propane site saved $22 a month, which speaks to kind of the fact that propane is more expensive, so that saved them a lot of money. The electric resistant site saved $40 a month. But as John mentioned, they could have installed the 240 volt unit, and so we don't necessarily recommend that people are switching between electric resistance and 120 volt. Retrofits cost $5,500 in the study. We estimate that this would cost about $4,200 at program scale, which is still a bit more expensive than installing a natural gas heater, and so units couldn't pay for themselves with that $7 a month savings. So we talked to consumers at 4 different points throughout the study. We ran a survey with their prior unit right after install in the early spring and then at the end of the study. That last bar that's showing overall was a question asked at the end of the study about general experience rather than since the last survey. There was no negative satisfaction. People liked the units. There were 2 3 out of 5 neutral ratings. One of these is from the household who ended up switching from their heater that I pointed out earlier with the highest level of consumption. And then one of the 3 out of 5 ratings was because that person experienced water loss when visitors came. So they would have a lot of people over for the holidays, and the heater wasn't a good fit for them for that. There's an increase in satisfaction over the study period, maybe because people got used to the units, maybe because the beginning of the study was during the winter when those units have to work the hardest to heat water. There was an increase in satisfaction from the old heater as well. There were a couple malfunctions over the study period. The manufacturers and the research team were able to troubleshoot with the participants and fix those. We asked people about whether they noticed a seasonal variation in performance of their heater, and 4 people said they did, meaning that the heater was performing better in the summer months. Along with the temperature and humidity that we measured earlier, the survey results correspond pretty well with that. More participants noticed a temperature change than humidity, and humidity change was noticed more in the summer. Humidity was almost always seen as a benefit, but temperature was a benefit or drawback depending. During the winter, it's not as much of a benefit to have the compressor decreasing the temperature of that room, but during the summer, that's pretty nice. 17 participants noticed noise from the heater. Only 1 person found this noise annoying, and they had a workshop directly next to that heater. So we don't recommend that people be working in very close proximity to those units. We asked people about their experienced hot water availability. All in all, there were no people reporting frequent runouts. and no people reported dissatisfaction with their unit's runtime. The most runouts were reported during the early spring survey, which was during the winter months. And 4 people reported that they changed their consumption habits to avoid runouts. 2 of those people were the 2 that gave the 3 out of 5 satisfaction rating. The other 2 reported that they changed their habits, but didn't mind doing so because it was easy enough for them. 2 participants reported being able to consume more water with their newer heater. And some participants really enjoyed the manufacturer app. There's kind of like a vacation mode and some other things on there. Others found the app a little hard to use.
Thanks, Dani. All right, I'll move along to conclusions and recommendations from this study, and then I can answer questions in the chat and answer any other questions that pop up. So first off, we found that these could be a good fit for energy efficiency programs and electrification programs in the Midwest, provided that space is not constrained and an outlet is present. That happens to be a good fit for many Midwest basements. You know, but going along with that, the units are expensive and decreased operational costs, but in terms of lifetime costs, without incentives, they would be probably losing customers money. So they definitely need to be rolled into programs that are providing incentives. You always want to look to see whether there is a shared circuit outlet, a dedicated circuit outlet, or an existing 240 line. Pick the one that supplies, you know, if you have the power available, use the unit that is right for that power. So 240 volt is preferred. If that's there, if a dedicated circuit is preferred, dedicated circuit outlet is there, use that. Then a shared, if there's a shared circuit outlet. And definitely if you know, we did the study for utilities, but if you can get that information ahead of time, it's certainly helpful when you go to the home. The manufacturers who saw the results of this study did basically say that sounds great. We'll start, you know, permitting distribution of these units in the Midwest, or at least exploring it, because they could provide enough hot water for, you know, 95% of the people in the study. There are some runouts at higher levels of consumption, and hot water consumption patterns. Participants changed them in response. And we did have one participant who actually got a different unit at the end of the study because their consumption just was way outpacing what the unit could provide. So we have some guidance, particularly in the installation guidelines at the end of this, which we're also releasing. We have as a PDF on our website that just gives here's the right case to install these. In general, don't install them in homes with more than 4 people. If there are 4 people, then they should have a dedicated circuit unit, or you need to go through the home and make sure that they have low flow shower heads and that their consumption is not, you know, they're not taking a lot of baths or like super long showers. If the existing water heater in the home fails to provide them with enough hot water and isn't, you know, obviously faulty or undersized, then that's also a good clue that they may not be a great candidate, because when these units run out of hot water, they run out for longer. We did see an increase in power consumption due to colder groundwater. It takes more power to get, you know, that cold groundwater up to the temperature that the hot water is delivered at. But we also saw that the units could perform well enough for most participants, for the vast majority of participants. One thing to look out for is that the room with the water heater needs to be large enough for the unit to have full functionality, however. Participants were satisfied. The participants who were dissatisfied either had runouts because they had a high level of consumption, or they were right next to the unit and the unit makes a little bit more, I wouldn't say it's louder than, say, a furnace, but it has more of an air conditioner type sound, which can be annoying to people who are close to it. It's not quite as noisy as an air conditioner. And it makes cold air. So, you know, if you're in an already cool basement and you're spending time in there in the winter because you have a workshop, you're not going to be very happy if that unit is making it even colder. It doesn't make it much colder, but a few degrees can make a big difference to people. The one thing to consider that we kind of touched on is that if you have a propane water heater, it's actually a good cost deal. So definitely encourage people with propane water heaters to switch because they will save money across the lifetime of the unit. Here's a rough overview of our installation recommendations. We have a much more detailed set on our website that are nicely laid out. So feel free to check that out after this. Thank you very much, everyone. I will go ahead and answer the questions in the chat. Let's scroll all the way up first. Ken Walls, that's right. Usually there's a dedicated electric outlet if they have a power vented natural gas water heater. That's recommended in, I think, the installation guidelines for the gas water heater. And so you can find those specific dedicated outlets for water heaters are in those places where there's a vented unit, power vented unit. Upsizing by 2 sizes. Water heaters typically come in 40 gallon, 50 gallon, 65, 80. So if you're looking at the existing unit and it's 50 gallons, then you say, okay, 50 to 65, 65 to 80, that's upsized by 2 sizes, or 40 up to 65. So you're going to want to upsize from their existing unit. Heather, we touched on this with the temperature and humidity and noise. In general, if there's even a wall separating it from somebody, the humidity and temperature impacts are not going to be noticeable. But if it is directly in a living space where somebody would be dissatisfied with some cold air, then they will notice it. We did have one gentleman who had a server rack in his basement and a little office there. And he actually liked it because the server rack was hot and this kept it dry and cool in that room. Okay, why would the 120 volt units activate their electric resistance so much less? Their electric resistance is actually undersized and small and really only there in an emergency. The heat pump has trouble on these units, has trouble running at low temperatures. And so it switches to the electric resistance, which can run at any temperature. It's not using it to like boost. It actually can't. It has to turn off the heat pump and turn on the electric resistance. We did not use IRA money. These were fully funded by the utility partners and program partners of the study. But they are, I believe, qualifying units for IRA money. So, if you were installing them and paying the full freight as a customer, you could tap that to get yourself a discount, and that would affect the economics for those customers. In terms of large enough for full functionality, it was, for the dedicated circuit units, I think the 50 gallon was nice for roughly any user. I would say a family of, or 3 occupancy residents and a 50 gallon dedicated circuit was a good fit. An 80 gallon, similarly, an 80 gallon shared was good for a 3 occupancy residence. And again, if it's 4 occupants, it can work at either of those larger sizes, but you just need to be careful about their existing hot water use and make sure that they are not high users, that they are lower users. Size of space. So the shared circuit units, which have a smaller heat pump, need 700 cubic feet, which, if you have 10-foot ceilings, then that's 70 square feet of ground space. And the dedicated circuit units, I believe, needed a little over 1,000 cubic feet. So about 100 square feet of space or a 10 by 10 room. With ducting or louvered doors, that effectively increases the space that they have available. So if you have like a utility closet that's too small, but it has a louvered door, which has vents on the top and bottom, then you can count the space from the adjacent room as well in your heat exchange area. And so, you might, between the two rooms, you might be able to make enough space for the unit, or have enough space for the unit. Any other questions?
Hi, John. I just dropped a couple of questions in the chat. Thank you.
Yeah, I see that. Okay, thanks. Oh, in terms of consumer education, definitely, making sure that the consumers understand that it's going to cool the space around them, that that this is a unit that installs on a 120-volt outlet and is a little bit less powerful, so they should be lower water users. In terms of outreach and education around the units, we did work with our utility partners to make as many recommendations as possible and give them that installation guide to try to prime them to develop their own materials. Obviously, we're not on the ComEd marketing team or the Consumers Energy marketing team, but A, we would be happy to work with them in the future, but B, we also think we gave them kind of enough ammo to build up some nice consumer education pieces to put out with these units. And could we go back to the chart with the 3 temperature sensors? Yeah. Yeah, this one down here.
Yes, yeah, exactly. Just from the bottom to the top, what's the temperature?
Oh,
scale?
yeah. Yeah, the top is 66 degrees and the bottom is 60. Well, this is 62, so it's probably like 61 and 67 at the very, very ends, or 61 and a half, 66 and a half. So it's about a 5-degree difference, 6-degree, 5-degree difference across the full scale.
Great, thank you. Thank you. I think while you're answering those, I think a few more questions came in through the chat.
Yeah, we don't recommend that you use this technology for a family of 5 or more. This gets a little like down into the weeds, but if you assume like an average amount of gallons per day of consumption of hot water, these units, their runtime gets longer in cold groundwater temperatures, and with enough occupants, basically they would have to run all day or more than the number of minutes in the day in order to make up the hot water needs. And so there are 120 gallon units that are not marketed for residential customers and are not 120-volt units. And you could get a heat pump water heater that's bigger than 80 gallons, but generally 80 gallons is kind of the top end of a residential unit. And then follow-up question with the IRA money. Are these qualified for IRA money? Now, they have certified UEFs and therefore are qualified. Do check the listed UEF of the unit, because I believe that is how the IRA, I think it might be how the IRA qualifies them, because it might be that they need to be EPA Energy Star certified. I'm not 100% sure. So definitely look at the listing of the unit versus the IRA qualifications, but they are qualified today. They're rated. Yes, these were $5,500 each, but we think that some of that had to do with just kind of the nature of the study. We had to do more electrical than you would have to do actually out in the world, because the flow of this was that we qualified people into it, trying to do a virtual walkthrough to understand fully their space and their situation, but that didn't always tell us everything. And so we'd get there and we go, oh, we need to make an electrical upgrade. Actually, this outlet is not going to work, or something like that. So 4,200 is what we estimate. And that's with them at the current cost and, you know, current like training level of installers. That being said, I don't expect that number to go down a huge amount. The lifetime of these units is, I think, 10 to 12 years, as listed in like technical reference manuals from states. So they won't pay back with that $7 a month, but they will pay back with the $22 a month from propane. And then when you factor in incentives, you know, if your utility puts $500 or $1,000, and then also there's IRA, you know, it's possible that you can be in a more favorable economic situation.
Thank you. Thanks for thinking about both of those.
Click back to that question slide. Anybody else?
Okay. Well, in that case, everyone, we may have reached the end of our questions. That was a really great presentation. I was looking forward to it very much because I saw some information from the preliminary study about a year ago. So I was really excited to see how this large rollout played out. Thank you very much to our presenters. Remember, from CREATE, we have 2 more workshops coming up later this week. You can find information about those at createenergy.org. And I think you can still register for those by emailing into Gabby Temple. With that, I think we'll say thank you one more time to our presenters and grateful to all of you for attending today.
Thanks for having us.
Thanks, folks. Great study. That was a really good presentation. Super interesting. I'm looking forward to reading through the rest of the report.
Thanks, Ken.
Thanks also for posting your summary and recommendations at the Slipstream website. That was really accessible and easy to see when I looked at those earlier. So thank you. That's great.
Thanks.